Good morning, everyone. Welcome to this morning's session on closure issues. My name is Jason Cumbers, and I'll be the moderator for this morning's session. As a reminder from what Chris said earlier, the speakers will have 15 minutes each, and then we'll be taking questions either in the app or around the room with the mic, so you can ask questions either way when the speakers each get done with their presentations. Our first speaker today is Ariel Terliski. He is a senior consultant with SRK Consulting in Argentina. Ariel is a civil engineer from the University of Buenos Aires with over 13 years of experience in computational mechanics in the oil, aerospace, and structural sectors. Welcome, Ariel.
Thank you, Jason, for making the introduction. Hi, everyone. Thank you for joining. And well, today I will talk about the modeling cover system for tailing facilities, integrating Idrus 1D and Python for enhanced seepage prediction, right? So, as being in the closure session, we are all aware of what a cover system is. Here we can see that below in blue, we have a waste rock, which can be potentially acid generated, PHE. And in order to do not have generation of acid, we may need to put a cover above it, right? You will see from this scheme that we have a lot of arrows, meaning there are a lot of variables as an input and output of our system. And using the guidelines of MEND and INAP, we will try to understand how to have a best performance cover, right? So, going straight to our work, we do numerical modeling, right? So, which are the inputs for the numerical modeling? We need to know the hydraulic properties of the materials. We need to know the geometry and the position at the climatic conditions that the cover will be up to. We will use Idrus 1D as a software to solve the unsaturated flow. And the outputs of our software will be the infiltration at the base of our system, the degree of saturation of the layers, and even the runoff. Why we need that output? In order to have some objectives. That objectives are to define if we need to put a liner at the base of our TSF, to use the degree of saturation of the layers to have the input for the geochemical model inputs, and also to understand the drainage system design. This can be done in Idrus, but the thing that we did is to integrate all this stuff and solving with Python and Excel so that we can run plenty of scenarios in very short time and make a lot of sensitivity analysis at the same way. So we will focus in one main thing in this presentation, which is the possible oxygen ingress to our system. In order to understand the oxygen ingress, which is the reason why we can have some acid generation, we need to understand that the degree of saturation in our common system is the main issue that we need to take a look at in order to see the oxygen ingress to the system. You can see from this plot that as higher we get to the degree of saturation, is less the oxygen ingress to our system. So, I will say it one more. It is important to understand that all our plots and outputs will be regarding the degree of saturation, as we know that if it is high enough, we will consider an 80% threshold to see if the cover has a good performance. We will take a look at that so that we know if oxygen is ingressing or not to our system. Here we can see a scheme of an Idrus 1D stuff. At the bottom of our scheme, we have the tailings PHE. We need to define boundary conditions. At this instance, we will say that the bottom boundary condition of our model is to have free drainage. Water goes out of the system. The water table will be below the system. And above the tailings PHE, we will have a cover, which will be non-PHE. For this theoretical example, we have considered also a tailing as a cover, but at this instance will be a non-PHE material. That means that we will have availability of that material, and we can play around with the thickness of the cover. Above of our cover, we will have the atmospheric conditions, which can be rain, which can be potential evapotranspiration, and we will define that variables in order to get the degree of saturation of our cover. So it is important to say that in this exercise, we are considering slurry tailings. That means that at the beginning of our simulation, we will have a fully saturated profile, which means the degree of saturation from 100%. Here, we use as an example climatic conditions, two different climatic conditions, which are cold humid or cold arid. So what we have is a 40 years database of information of the precipitation and evapotranspiration of our site. And what we do is to define the mean annual precipitation on each of the scenarios, and we will find from the 40 years database the year which is closer on that annual base to the mean annual precipitation, and we will use that as an input. The same for the arid scenario. So here we have the information of the rain, the precipitation per day as for an year, for the arid and for the humid scenario, and what we will do is to run our model for at least 5 years, and what we will do is to cycle this information of the daily precipitation through the 5 years, right? You can see from here that the humid and arid scenarios are not as different, but it is 40% higher, the humid one. But when we go to the potential evapotranspiration, the arid scenario has at least 5 times higher values. So that means that we may expect quite different results. So, going to the results, what do we have? We have the degree of saturation as a result, as I said before. In here, you can see to the left the scenario of a cover in a humid scenario, and to the right with an arid scenario, right? We have as an x-axis the degree of saturation, in the y-axis the depth of our system, and the line plots, which go to light to bold, means the advance of time, and we see how the profile changes according to time. At the beginning of our simulation, we will have the dashed black line, which means it will start from approximately 1 as a saturation. And as the time goes by, this is the first 2 years of our simulation, you can see that the humid scenario starts changing, of course, but it seems that it is getting to a quasi-steady state. In the other side, the arid scenario does not. So if we continue our simulation and we go to the last 2 years of our thing that we are simulating, we will see that to the left, in the humid scenario, we get to a time, which is almost 3 years, that we get to a quasi-steady state scenario. And all the degree of saturation changes across the year, but it is almost above the threshold of 0.8 as a saturation, right? And to the right side, we can see that the arid scenario is still drying out, and the value and the objective of having a saturated cover is not being obtained. Okay? This is like the usually line plots that we used to have, but now what we do is to make this kind of plot with a 2D scheme. This means that to the left, we have, again, the humid scenario, to the right, the arid scenario, but now, in the x-axis, we have the time, in the y-axis, we have the depth, and in order to understand which is the saturation of our profile, we play around with the color plot. The important thing here is that the dotted hatch is when we are getting to a value which is above the 0.8 threshold, and you can see to the left that across the 5 years we are getting the higher degrees of saturation, which is nice, but in the arid scenario you can see that it is drying out, and each time we are getting less water inside. This is like the same results as in the line plots, but now we can see it's just in one plot, and we don't have that amount of lines at the same time. Now, as I said before, the opportunity that we have when having this automated by Python is to change a lot of variables very easily, and at this time I will show one which is easy to understand, which is what happens if we update the permeability of the cover. Of course, if we decrease the permeability in 2 orders of magnitude, we will have a completely saturated cover across the 5 years of simulation, while when we increase the degree of, the permeability, we will see that it dries out even before the year, okay? So let me say that these both figures, it's for the humid scenario, right? Although you have a humid scenario, if you have a high permeability, it will dry out in the same way. And finally, the other thing that we can do with our tool is to play around by making a multi-layered cover. That means that we will try to find which is the best performance cover, and in this example, we find out that the cover number 3, which is more explained in our paper, have the best performance as a saturation. So we just adding a less thick layer, and then below that another cover which is not as good as the first one. We can see that the oxygen ingress will be limited in the upper side. So that's what it was about. Some conclusions and comments. The cover example, we have daily climate values have a significant impact in our model. Instrumentation and control may be needed only in the active zone, which is the one that we show in the line plots for the humid scenario. We can say that 2-layer cover profile can be done to minimize best performance material availability. And the main issue is playing around with Hydrus 1D plus Python, which means we can run a large amount of Hydrus 1D models in a short period of time, and we can perform sensitivity analysis easily by varying conditions, such as hydraulic, climatic, deposition, etc. And that's it. Thank you.
Are there any questions for Ariel? Don't see any in the app. Anybody in the room have any questions? Back.
I can try, Tony. I'm just wondering, how did you calibrate the model to existing conditions?
Sorry?
How did you calibrate the model to existing conditions?
We can use instruments, as I said before, at the top of our cover to understand if, as the time goes by, the degree of saturation is like similar, right? We use a lot of parameters inside of our material properties, hydraulic properties, and that's a way of doing it.
Okay, thank you.
Okay.
I wonder if you use like your boundary condition for the model. Have you used like the climate condition, and did you have problem with convergence with Hydrus 1D? Or you were more in the steady state?
Yes, we did. As I said before, we have a 40 years data set of climate conditions. We choose the mean one. And yes, we have to deal with some convergence issues, but we find it out the way to get it and get the results. Yeah.
Do you have an approximate cost of what your cover depths range? You had showed a 4 meter and then a 2 meter cover cost. Do Do you have anything
Just
associated?
remember that at this exercise, we play around with tailings non-PCA, which means that we will need to deposit that tailings somewhere. So it means that this is a cost-effective solution, having this kind of cover. But relying to another type of cover, which are not tailing PHE, I don't have the answer for that.
So do you have a moisture content in your cover material that you're trying to achieve for cover placement?
Yeah.
Okay.
Thank you.
One more there in the back.
Just wondering, the Python script that you're using, is that something you had to write, or are you relying on a code from a library elsewhere?
We write it down.
Thank you.
Yep.
Thank you, Ariel.
Thank you.